Hello guys, welcome back to episode number 7. So today is very special video because this is the last video of our pre-layout simulations, right? And also today we're gonna discuss about the power analysis and considering the current situations, how we are trying to build electronics or the VLSI chips for the portable devices. Power is the most important thing, right? So if you have this concept, then you can for sure work on low power design, and currently low power design is in the news, is the hot topic. Actually everyone need their engineer to be a good verse with these power concepts. So as a beginner, I think this is the fundamental, so please concentrate. And if you are liking my tutorials, then please like now only. This is the only currency, the likes, which keep me motivated. So I'm hoping you have done it. So let us start it and let us open our Xschem. So I have opened my Xschem. So I am here ls, and I'll go to my this which I have created pre-layout simulation, c2 pre-layout simulation ls, and then launch our Xschem inverter schematic test. This was a test bench we have created 2 or 3 episodes before, right? Okay, so here everything is set up. I don't think we need to change anything, but just here what we'll do, we will just eliminate this DC simulation, because no way we are gonna do a DC simulation today. For power, we need to do the transient simulation, because the power formulae, the average power formulae, if you remember, it is the integration of your current. Let me try to flash it here. So I got something. So this is the formula, just ignore everything else here. This line here, so this is the formula of average power, guys, right? And for our case, when I'm gonna simulate, everything will be clear. So that's why we need a time component, and that's why the transient simulation, not the DC simulation. Just remember this formula, right? Or I'll flash it again when it is necessary. So okay, so that's why I'm just removing it. If you don't remove also, there is no harm. Just we need to do set plot and select the plot, perfect plot, otherwise our ngSpice will be confused. That's the issue only. So other than everything is fine. Okay, so let's do the, okay, before netlisting, let me check the size of inverter, because size also have some important things to do with our power simulation. So if I do Q, and I think I changed in last video to 8, so let's get back to the old one, or the minimum size inverter. And the minimum size inverter have the PMOS of 2, PMOS of 2 and the NMOS of 1 size. So I'm getting back to the minimum size or the reference inverter. So this is the minimum possible size in this technology. So I have restored it. Go back, yes. Okay, now let us do netlist. And in the netlist, I can't see the netlist window because it is not enabled here. So view show netlist window and the netlist, and I can see it. And here I'll confirm if everything got changed. Yeah, my NMOS is 2, my PMOS is 2, NMOS is 1, and save it, and then do the simulation. So simulation is underway and done. And let me see how many plots we have, and see, these are the plots you have. You have, like, here current need to be, because the formula of power is your voltage into current. So we need to know the current, and which current from the power supply, from the VDD. You can say here we have another voltage source here, V in. So V in might be providing you some current. If there is a power source which is not providing you any current, for example, if we have a power source, not actually, it's wrong, voltage source, right? So if we have a voltage source of 1000 watt, not watt, sorry, 1000 volt, but it is providing you 0 current, then from that voltage source we are consuming 0 power, right? Because V into I, if I is 0, then there is no power. So in the input node we have a voltage source, but for the most of the case there would be a 0 current. There would be some nano ampere or femtoampere of current going through the gate, but in most of the case we can ignore that. So that's why this power source I am ignoring, not power source, voltage source, but we will take only this voltage source. So in ngSpice, what this is signifying is that the current drawing from that voltage source. Okay, so if I just try to plot my VDD hash branch, and see, this is your current, how the current is flowing, right? And you can appreciate another thing if I plot our V out also with this. So let me do this thing. Let me plot, okay, let it be plotted here, and let me plot V out also here, V out. So see, this red line is your power, like current, how was the current we are drawing, right? But this current is not visible here because see here, we have 1.8 of the scale of y-axis, but here it is in micro, so to see both of them together, what we need to do, we just need to scale it up. So we need to multiply it by 1000 because it is in micro, and then probably we can see something. And yeah, you can see something here. Let me close it here. So see, we are drawing the current which is negative, and in the current sense, negative means the sign convention only. You understand, right? From probably from the voltage source, if something is going out, so as a sign convention is taken as negative, but it's all okay. There is no physical significance of negative sign here. We'll make it positive later on. Okay, so anytime we are getting a high in our output, which imply we are charging our load capacitance, right? And who will charge your load capacitance? Some charge need to be stored in your load capacitance to get it charged to the high voltage, and that charge is provided by your VDD power or voltage source through the current VDD branch. So that's why any time we are at a stable zone, for example 0 1 0 1, we are not charging or discharging our capacitor. So that's why only during charging we are seeing a power pull here. But you might be asking me here we are discharging our load capacitance. See, here your load capacitance is charged to the top value 1.8, and we are discharging it to 0. So that time also there is a flow of current or electron, that's why we can discharge it. But if you just remember your MOSFET, not MOSFET, inverter, then you can see we have a PMOS here. Let me just flash it here again, this schematic. See, you have a PMOS here, right? Let me make it little bigger. You have a PMOS here, you have a NMOS here, and here we have the load capacitance. So anytime we are charging, we are directly connecting our load capacitance with VDD. So current is flowing from here to the capacitance, so we are drawing some current. But during the discharge cycle, your PMOS is off, your NMOS is on, and we are discharging it through the NMOS to the ground. So for the half the cycle, whatever current we drawn from VDD, we are discharging that current only. So in other way, we are not drawing any new current or any new power. So that's why during your discharging phase, we are seeing no power. If we zoom in, there would be some current for sure, because if you just remember power theory, your inverter power theory, you might remember that we have three components in the power actually. One of the component is your dynamic power, right? And dynamic power is this. Whenever we are switching, we are having this dynamic power. And about the dynamic power, in my theory class, in my VLSI interview tutorial series, it is flashing here or here, I have already explained it. I haven't explained the next two components of the power, and those are your static power and the short circuit power. I will explain them in my future theory video. Here I won't be explaining them, right? You have book, you can refer if you want now. But in today's power analysis, we will analyze the power together. All the three components will take together, right? And how? Because we will do the integration of our current. Any current we are drawing in any phase of the operation, dynamic, and you can say this is dynamic, but this is also a short circuit power also in some term. Because if you remember your short circuit power concept, then short circuit power concept is coming only due to non-ideality of our input clock, right? And here we have simulated with the non-ideal clock only, because see here your clock have some significant rise and fall time, and due to that only we have a situation when your both PMOS and NMOS are on, so we directly have a path from VDD to ground, and that is called short circuit. So here this current drawn is due to the two of the component, that is dynamic due to your charging of capacitor and due to the short circuit. And then the third component, which is your static, and that is here actually when one of your NMOS or PMOS is off. So ideally there would be no current drawn, because if I again go inside, again I go in inside this, then if one of these off, then that means there is no path from VDD to the ground, or if your load capacity is already fully charged, then there is no current flow. But still we have some leakage current, and that's why that static power dissipation come into picture. So you can refer your theory, but here in the simulation by default actually, because we will do integration from here to the full period, right? So we will take care all the current here. For example, see here we have something, we can see some non-duality in the current, right? This might be of limitation of the tool or something else, but whenever we do the integration, we will take everything into the consider. So all the three components of the power will get considered today. So to calculate the power, what we need to do, we need to again see the power formula, and let me flash it for you, and let me keep it can I keep it here like that? Probably yes, only this formula. Okay, so see, power means voltage into current. We have the current, and let's do one thing, because current is what is have the dependency on time. So let us do the integration of current first. So what I'll do, I'll do measure and a value from transient analysis whose name would be current integration, and we need to do integration. So Ngspice have the function to integrate. If you don't know how it works, you can again refer to your manual, you can go there, you can know everything. So integration, and what we gonna integrate, we gonna integrate this current branch, VDD hash branch. We need to set the limits of our integrations. So limit of our integration will directly come from this information. Let me go to our schematic. Yeah, so limit of integration will come from here. See our if you just remember your pulse, then we have given some syntax, and this is your period. So here we have 20 nano as our period. So we can, there are many periods, 0 to 20, then 20 to 40, right? So what we'll do, we'll take the second period, because during the first period, whenever we are starting our circuits, there are some non-ideality mostly, so better to take the second period. And luckily we are also running our simulation here, you can see from 0 nano to 40 nano, so we are actually completing the second period also. So I will do what I'll do from 20 nanosecond, and there I faced one issue. I'll show you what the issue I faced, error I faced actually. So okay, let me write from 20 to 40, and I'll get error. And error is that, see, I am trying to do it from 20 to 40, but below it is showing me something like non applicable or some different thing, and this is because we need to give the correct scaling here. So 20, what does 20 mean to the Ngspice? Nothing, right? So we need to let them know it's a nanosecond. So it is like we need to give it in exponential form. So the format is like that. So now it is nanosecond and E minus 0.9. Okay, and now this is the perfect. So this is the current integration in one of the period. So if we go to our formula, then we have done the current integration. To make it to power, what we need to do, and that is we need to multiply it with our VDD, and VDD is constant 1.8. so this is our variable. Okay, so I'll do let power instantaneous, because before we divide it by t, it won't be average power, it will be instantaneous power. Actually not instantaneous power, but yeah, it's a intermediate. So let me write intermediate equal to the current we have just got from this integration into VDD, which is 1.8. let me print this power intermediate, and yeah, perfect, this is. And so we have done everything, just we need to do divide by T. So what I'll do, I'll directly print our power intermediate divided by T means the period, and period is your 20 E minus 0.9, and this is your power, average power dissipation of this circuit, and that is a huge one. Actually it is you are again seeing a minus have no physical significance, as I informed earlier. So it is around 81 microwatt for a single inverter. If you, and single inverter means two MOSFET, and if we example millions of MOSFET, just see how much power will be dissipated here. And this is becoming dirty because of one of the factor, and that is because of the CL. We have taken a large CL here, 0.5 pico, right? And we'll come to this later, how to reduce the power. But before that, see, power dissipation, this is for one period, for one switching activity. So that means if we can do the switching activity for 5 times, then we will invest 5 times the power here we are consuming. So that means if we can reduce the switching activity, then we can reduce the power consumption, and there the architecture come. Actually, the better the architecture, the better the power efficiency, power performance of your circuits. If I want to give you a little example, like there are many architecture, BBQ architecture, RISC, ARM, x84, and we don't have the in the position to compare them. But if we wanna give you a small example, and that is, for example, we have a adder, ripple carry adder, and also we have a adder which is called look ahead carry adder, something like that. So if we can compare both of these two, we can know which or through which architecture there is more switching activity. So if a architecture or a design perspective give you less switching activity to get the desired result, then we can use that to save our power, because we are getting the same answer with less switching activity, with less Boolean algebra in rough sense, or less complex Boolean algebra. Okay, I'm not going into deep. There are great books, as you know. I always refer this book in all video I am showing you. This book is like everything. So there all details are there. I'm not spending much time here in this practical lab classes probably. Okay, so this is your power. So now how to reduce your power, because reducing the power is the main concern here. If it is, then one is reduce your CL, and we know CL is dependent on the load capacitance, and load capacitance is indirectly or directly depend on the layout of your inverter, in your inverter and the load, because this load capacitance is coming from the next layout or next device. So if we can do layout efficiently, and there the importance of layout engineer, right? If you are designing standard cell library, and if you can design it more efficiently, reducing the capacitance, because load capacitance is a huge factor in like contributing to power effect. You are not sure, okay, let me reduce this load capacitance, and we will see how this power consumption will reduce. So let me do one thing, let me copy this every codes here. Okay, so I have written everything here. This is power, your average power, and this is like to fasten things up. So let me do one thing. What I'll do, I'll just reduce this capacitance here. So if I reduce it to, for example, 0.1 picofarad, okay, netlist, save, simulate, simulate, and then paste this. Everything is perfect. And then to get the power, what I'll do, we'll do print. We need to this current integration, okay, we need to multiply it with 1.8, and then let me use braces here, and divided by the time period, which is 20 E minus 0.9, and see how your power got reduced here. Average power, it is minus 3.2, so that is proved. And you can also see here, if we increase the size of our inverter, and why we increase size of our inverter? To speed things up. So if you want a speedy circuits, then probably you need to increase the size of this NMOS and PMOS, and if you increase, then your power again shoot up. So these both things go in different direction. A efficient circuit need more bigger circuit size, but then again your power budget will increase. So there we need to maintain a balance. Actually, you can do this task, just increase the size of this inverter and see how your power get jump up. Now see, if we can't do with the CL is constant, then there is a very easy way, and that is reduce your VDD. Reduce your VDD. Here VDD is 1.8. if it become 1, for example, and see here we are multiplying it, so if it become 1, then for sure our power, like from easy maths we can see. So this is a way, another way to reduce the power consumption. So in summary, mostly we have three ideas to reduce the power consumption. One is architectural changes, reduce the switching cycle, switching activity to reduce the power consumption. Another is reduce the CL, try to do your layout efficiently, because in CL we know we also have a component which is coming from the wire. Here is the inverter, there is another inverter. How you connect these two? If you use a long path, then there will be more capacitance, more power consumption, so you can reduce that too. And third would be, if you can reduce the voltage, right? So these three, there are many other way in advanced design, but as a fundamental thing, as a starter, this all are the things. So try these things out, and the good news is that we also have our Telegram group. So in Telegram group, not group, a channel actually, and in that channel you can comment out any issue if you are having in Telegram, in this comment section also. And you as a community, we gonna help each other, because I won't be here most of the time, right? So those who have done these things, if you see somebody is facing some issue, then please help them out. And from the next video we'll start our layout journey. And before going to layout journey, what we need to do, we need to know actually that many things, like layer stacks, other things. So in next video I'll do those layer stacks things. Next video will out in next 5 or 6 days. There are delay, I know, but I can't do anything. So till then, take care, keep learning, and if not subscribed, consider subscribing. Bye bye.